All the stars that shine at night are driven by fusion energy. It's what powers the universe. The challenge is, how do we take that enormous object and that enormous power and recreate those conditions here on Earth? If we can do that, we can supply civilization with the energy it needs to develop in a way that it removes the scarcity of energy as a factor in how we develop as human society.
Hello, I'm Simon Mundy. I'm a journalist at the FT, and I recently spent 2 years travelling through 26 countries exploring the race to respond to climate change all over the world. In this film, we dig into one of the hottest and most controversial topics within the push for cleaner energy, one that has received a burst of fresh publicity in the last few months: fusion power. Let's begin in the south of France with what is, by many measures, the biggest and most expensive scientific experiment in human history. This is ITER, or to give it its full name, the International Thermonuclear Experimental Reactor. ITER is a joint project among the world's superpowers, trying to harness the awesome power of nuclear fusion to usher in a new age of safe, clean, and massively abundant energy. Together, the EU, US, Russia, China, India, Japan, and South Korea have contributed tens of billions of dollars and thousands of scientists to the project. Its origins date back to 1985, with a historic meeting between US President Ronald Reagan and Soviet leader Mikhail Gorbachev. Since the 1940s, scientists from their countries and others had been developing enormously powerful bombs using fusion energy, which were many times more powerful than the weapons dropped on Japan in 1945. In Geneva, the two leaders set out a vision to collaborate on fusion power for peaceful purposes.
Je suis particulièrement heureux de vous accueillir aujourd'hui pour la signature de l'accord international ITER.
It took years to gather the full international coalition behind the ITER project, which was formally launched in 2007. In the 15 years since then, vast sums have gone into building a fusion reactor in the French region of Provence, a huge structure that will be taller than Paris's Arc de Triomphe, covering the area of 60 football pitches. Progress has been slower and more difficult than anticipated.
The idea, when it was formed, was to bring, cultures and nations that have been in the past sometimes at odds with each other together. In fact, it was born between Ronald Reagan and Gorbachev. And then more parties, more members joined. So it is a place of peace in some sense. This being said, of course, there is also some complexity coming with an international collaboration, with having, some degree of politics associated. Okay, some compromises must be made. So it is not, the most efficient of the organizations that you can imagine to create an object of the kind, but it is part of its purpose. Projects like this, where you do sort of frontier research, go through moments of crisis. Sometimes the moments of crisis are of managerial nature, organizational nature, sometimes are of technical nature. Building a device like this always comes with big technical problems, even in the creation of this research infrastructure. So this is my priority now. It is to resolve these technical problems. This is a problem that came because companies that were engaged in the production of some components that they never did before.
But hold on a minute. What exactly is nuclear fusion? Well, first of all, let's be clear about what it's not. This is different from nuclear fission, which involves splitting atoms apart. That's the reaction triggered in the bombs dropped on Hiroshima and Nagasaki in 1945, and also the reaction that powers all the nuclear reactors operating in the world today. Instead, nuclear fusion involves smashing atoms into each other with such force that they fuse, releasing enormous amounts of energy in the process.
First, we know it works because it's what powers the universe. All the stars that shine at night are driven by fusion energy. And fusion is a process, by its very name, you can sort of guess. You take two small objects and you push them together, they fuse into a bigger object. And then the equation, most people maybe don't know physics equations, but they've heard E equals mc squared, which is energy is equal to the mass times the speed of light times itself. That speed of light's a big number. So if you make a little change in mass, you get a big amount of energy. So when you fuse these two small objects together to make a heavier one, there's a little bit of mass difference, and that shows up as energy from the reaction products. And that's what we need to make heat, to move turbines, to make electricity, or to make hydrogen for transportation fuel. And that's the basic idea. We use this mass change, and it's a nuclear force that we're using, to make a large amount of energy from a very small amount of mass.
Following the first fusion experiments in the 1930s, fusion laboratories were established in nearly every industrialized nation. A major breakthrough occurred in 1968 in the Soviet Union. Physicists Igor Tamm and Andrei Sakharov, inspired by an original idea from Oleg Lavrentiev, introduced a toroidal magnetic confinement device that they called a tokamak.
To make energy from all this, we need a machine that can reproduce the incredible power of the process that powers the sun within a single building here on Earth. The most popular model being developed by scientists at ITER and elsewhere is the tokamak, a term dreamed up by Soviet scientists in the 1950s. It describes a donut-shaped structure with very powerful magnets known as superconductors in the middle and around the outside. The idea used in most tokamak projects is to take two different types of hydrogen and mix them together in an extremely hot plasma, that's the fourth state of matter, in which charged particles float around in a kind of soup. One of those isotopes of hydrogen is called deuterium, which has one proton and one neutron in its nucleus. The other one is called tritium, and that has one proton and two neutrons. The magnets keep the plasma suspended in a vacuum without touching the walls of the chamber. When the plasma is heated to a high enough temperature, the deuterium and tritium atoms start fusing with each other to form helium, which has two protons and two neutrons in its nucleus. That leaves an extra neutron, which gets fired off into the walls of the reactor, generating heat. And that heat, if all goes to plan, can be used to generate enormous amounts of electricity. Dozens of tokamaks have been built over the years, and many of them have generated fusion reactions. But none has yet given off more energy than it takes in, what is referred to in the industry as net energy gain.
It's the first time it has ever been done in a laboratory, anywhere in the world. Simply put, this is one of the most impressive scientific feats of the 21st century.
In December 2022, scientists at a US government facility announced that they had achieved that milestone for the first time in history. Instead of a tokamak, the team at California's Lawrence Livermore National Laboratory took a very different approach to fusion. They used a massive laser array to fire 2 megajoules of energy at a tiny metal sphere containing deuterium and tritium. That triggered a fusion reaction that gave off 3 megajoules of energy. That increase meant that a fusion reaction with net energy gain had been achieved, but it's far from clear how we could build on this to create a working power station. Those lasers consumed more than 300 megajoules of energy, over 100 times more than they fired into that metal sphere. So while net energy gain was achieved at the fusion stage of the process, the system as a whole ate up far more energy than it gave out.
There are very significant hurdles, not just in the science, but in technology. This is one igniting capsule one time. And to realize commercial fusion energy, you have to do many things. You have to be able to produce many, many fusion ignition events per minute.
At ITER, scientists like Valentina Nikolaeva are hoping that after so many years of work, they may yet achieve the elusive goal of net energy gain in a way that would provide a blueprint for fusion power plants that could be built in large numbers, generating vast amounts of energy for households and businesses all over the world. Her decision to work in nuclear physics was inspired by her father, who took part in the response to the nuclear disaster at Chernobyl in 1986.
My question was like, can we use something different? And he mentioned that in principle, the three main parameters are sufficiency, sustainability, and safety. We can have something even more sufficient in theory and much safer. So it's not fission of very heavy nuclear, but fusion of very light nuclear, so that we don't have strong radiation, we don't have radioactive waste, and the fusion fuel can be taken just from the seawater. So in this case, we would have a safer source of energy. That's what we are doing here, trying to build this large-scale machine to prove and demonstrate wave to have an efficient fusion reaction, which means that plasma will heat itself. So the produced energy will be 10 times more than input energy.
If something went wrong, it stops. It just stops. There's no potential for it to go out of control. So and from the reaction itself, the byproduct is helium. We fill kids' party balloons with helium. It's safe. I mean, it's really such a wonder. You can't imagine why we haven't done it before. Well, it's really hard, and we have to work hard at it, and I think we will succeed.
In any circumstances, unlocking such a powerful new source of energy would be a massive development for human civilization. But as we grapple with the worsening climate crisis and the need for a rapid transition away from fossil fuel energy, the debate around fusion power is gaining new intensity. Some say that the priority has to be doubling down on the low-carbon technologies that are already available to us, such as wind and solar, and argue that fusion power is a wacky distraction that will always be decades away from becoming a reality. But to others, fusion looks like a potentially game-changing long-term answer to the twin problems of climate change and energy security.
It's a solution to the energy transition, it's a solution to energy security, and I think it's within reach within the next sort of 8 to 10 years if people pull their fingers out.
A lot of collaboration now is starting between the public labs and the private companies, and that's going to drive us towards commercialization, and that's what I personally find very exciting.
We will need multiple companies that are successful, and I'm very convinced that that will happen in the industry. Yeah.
When someone gets electricity onto the grid, or even when someone shows that they can get more energy out than they've put into fusion, the whole field is just going to blossom and it's going to attract more investment.
While the intergovernmental project at ITER is by far the largest scale fusion project in the world, a growing number of hotly funded private sector startups are betting that they can make faster progress. They've been deploying a range of approaches to fusion, from lasers to projectiles fired at enormous speeds. But so far, the bulk of investment in this space has gone to companies using magnetic forces to create fusion reactions. Among them is Tokamak Energy, a short distance to the southeast of Oxford. For a fraction of a second in early 2022, this machine behind me contained the hottest point of the entire solar system, 100 million degrees Celsius. That's about 5 times hotter than the center of the sun. And that was just one step towards the dream that's driving this British company, unlocking the power of fusion energy.
This is a huge milestone for us. It's the highest temperature, plasma temperature that's been measured in a spherical tokamak, and it's also the highest temperature that's been achieved by a privately funded fusion company. So yeah, we're pretty proud of that, and it's just a step on the way to continuing on with our experiments with trying to create the conditions where fusion can happen. My interest in fusion started when I was doing my GCSEs. In school, we were lucky enough to have a fusion scientist come and give us a talk. So we kind of learned a bit about fusion in our science classes, but on a very kind of physicsy level, whereas this talk showed us the technology and the reactors and this kind of thing. And just seeing this kind of like scale of it, I really like doing experimental physics, and it's a massive experiment to be able to work on. I was like, yes, I want to work on one of those. I wanted to get into this field and do cool physics, but also hopefully make a difference.
Hannah is one of a large number of young scientists who have been drawn to this field in the UK, which has emerged as a significant hub of activity.
The UK has invested heavily in fusion for the last 50, 60 years, and now we have a regulatory environment that enables commercial development of fusion. Well, I think private investors have become much more interested in fusion because of technological advances, like with the superconducting magnets, and also with AI control systems and so forth, and with advanced materials coming through. So rather than it being something that's purely the preserve of the government laboratory, it becomes accessible to privately funded innovators. And as we know, the private capital will demand very rapid progress, very challenging milestones. Not all the private ventures will succeed, but those that do will have a big opportunity as fusion comes closer to commercialization. I think now's the time for fusion to move essentially from government laboratories into private companies, a bit like space launches 20 years ago, where NASA ended up working with SpaceX to develop the next generation of space launchers because it was basically too slow moving itself to make the progress necessary.
And as we followed the large and fast-growing sums of money flowing into the fusion space, it took us to Boston, a major US hub for both technology and financial investment. Cracking the fusion puzzle would create a brand new commercial offering with a vast potential market. And for a growing number of financial investors in cities like Boston, that is starting to look like a seriously lucrative opportunity. One of the most high-profile investors in the green energy space is Breakthrough Energy Ventures, founded by Bill Gates and backed by other billionaires from Jeff Bezos to Masayoshi Son. Phil LaRochelle, who's been leading Breakthrough's investments in this space, says that fusion is one of the most exciting investment opportunities around.
So we have about $2 billion under management right now, close to 100 companies. And we tackle the 5 biggest sectors of emissions, which are agriculture, buildings, electricity, manufacturing, and transportation. Well, fusion I would put on the extreme end of risk and reward. So to talk about the reward, I think people have understood for a long time, since Eddington kind of explained what was happening in the sun in the 1920s, that this was basically the way that the universe got its energy. I mean, well over 99% of the useful energy that has ever come out in the universe has come from fusion. People did fusion in the 1930s. One of Rutherford's students, I think, kind of won the Nobel Prize for it. So doing fusion is just accelerating one thing into another, and with some probability, some of them will fuse. The thing that's hard is to get energy-positive fusion, and so that's what people have been working on for almost a century. And so, the prize for fusion is, if the Industrial Revolution was a 1,000-fold increase in energy density, then this is a 1,000,000-fold increase in energy density above that, and we have so much potential fuel of it that it could basically last forever. And then when you do the energy balance, it looks like the fuel is basically trivial compared to the amount of energy you get out for it. So the real payoff for fusion is that the fuel can be infinite, free, accessible to all, and potentially has no carbon emissions. And so when people ask me, why is it that you should be excited about fusion now, or specifically the magnetic confinement approach to fusion, I say, well, it's kind of the same reason why you should have been excited about computers in the 1940s when someone invented transistors at Bell Labs, right? when you had to make computers out of cranks and then vacuum tubes, you could only go so far, right? You were never going to make an iPhone out of vacuum tubes. But the people who understood the science of computers and understood the potential for computers understood that if you could replace a vacuum tube, which is kind of big, kind of clunky, breaks a lot, is slow, generates too much heat, with a much better equivalent, then all of a sudden the scientific curiosity would kind of change the world. The same people are looking at fusion, and they're saying, hey, we understand how these machines work, and if we had a much better magnet, then all of a sudden maybe this goes from science project to kind of world-changing commercial technology.
One of Phil's biggest bets to date has been on a Massachusetts-based company called Commonwealth Fusion Systems, which has raised about $2 billion for its technology using a new class of superconducting magnets.
This tape has a crystal in it that makes it a superconductor that doesn't care really at all about the magnetic field. So this material science innovation meant that if you could take this material, which is not a magnet, it's just a flimsy thing, and learn how to build magnets with it, invent magnets on it, that those magnets could go to much higher magnetic fields than before. And that's what CFS did, is we took material like this, and there were some other innovations that had to happen in this material, and then invented a whole class of technologies that turned this into a magnet that's double the magnetic field of what happened before. That's generally useful, but when applied to fusion, that fact that it goes like the magnetic field to the 4th power, that's a factor of 16. So if you change something by a factor of 16, right? Imagine if you're driving your car and it's 16 times faster, that a 20-mile-an-hour drive suddenly turns into a 300-mile-an-hour drive. Like, that is a huge deal. And that made these tokamaks, really, really attractive to push to that final little factor that's needed to make more power out than in, and to make fusion power plants in a commercial and economic package that you could build a product in that you could scale. And that's what we're doing.
So we're driving to a little place called Devens, Massachusetts, about an hour outside Boston, to visit a construction project that's altogether different from any other that I've visited before. This is where Bob Mumgard and his team at CFS say that in the next few years they're going to create a fusion power reaction that gives off more power than it absorbs. That's something that scientists have been pursuing for decades. These guys say they can actually make it happen.
This is the spark construction. So this all was a year ago a field, and now what we're building is the actual spark machine. So this is the building that will hold the spark machine, and actually standing where there'll be power supplies and transformers that will manage the power in and out of Spark. Spark is a demonstration, right? It is an integrated demonstration that we can create the conditions that are necessary for fusion to work, meaning we can get the temperature, the density, and the insulation, the confinement, all at the same time. If we do that, we get more power out from the plasma than went in. Q greater than 1, net energy, break even, those types of things. That's been a huge goal. And that is when you actually go from being a science project to being something that is a power plant-like thing. And then in 2025, we'll aim to turn it on, meaning like make the first plasmas on the path to net energy soon thereafter. So that's a pretty condensed timeline when you think about us buying the site in 2021 and having a working fusion system making more power than in like 2025. So that's like 4 years. This is like what happens when you shrink the scale and you put it into a very, very focused startup-like organization. So, this is impressive scale, but like this is a scale that you could build around the world, that we build things around the world every day at this scale. And this is, 1/10 the scale of the ITER construction site in France, which is building a tokamak to do net energy on the same sort of physics that we're doing with Spark, but without that new magnet technology.
So amid all this excitement, how soon could commercial fusion power actually become a reality?
We're now at a place where the science and component level advances and the capital available now, I think for the first time, makes it realistic that we might be able to have commercial fusion reactors, knock on wood, by the 2030s, I think. Maybe sooner, but I think 2030s at least you kind of have a believable story that if we tackle some challenges, it might happen.
If you're talking about making electricity, we could make electricity in the presence of fusion power now. If you're talking about a plant that generates electricity more than it takes to run the plant itself, 2050s probably. If you're talking about 1%, 5% of the world's electricity capacity by fusion, you need time to develop an industry. There have to be successive generations. So probably I would love for it to be during this century, but probably toward the end of this century till you could get a real fusion economy going.
You have to have a robust system of drivers to enable that. So, probably decades.
We're looking at a pilot plant delivering power to the grid by 2032, and then scaling up for global deployment by 2040. So this is a potential solution to the challenge of deep decarbonisation. 2035, 2040, out to 2050 sort of deployment time.
I don't think it will happen in my lifetime. It's when I started this, I thought so. I thought we would be able to make it. I see that it has degrees of complexity just by the nature of the process. I've started working in order to address the problem of global warming, but I don't think that the fusion will contribute in the short term. We understand that global warming is a problem now.
If you want to make a difference on climate change now, you're going to have to ask people to make a change in their lifestyle. Energy efficiency likely isn't going to be enough. For me, fusion, if we do make a choice now to impact climate change, there'll be a sacrifice. Fusion gives the hope that that sacrifice doesn't need to be forever.
Fusion power is not going to make a meaningful impact on the climate crisis or on energy security in the near term. But an impressive number of leading scientists, entrepreneurs, and investors are making serious commitments in search of what could be a major breakthrough for the long-term future of human civilization. And that, for me, makes this one of the most intriguing areas of technology to watch. This was the first film in a 3-part series. Please make sure to like, comment, and share.